Anti-aliasing filter. An anti-aliasing filter AF is a filter used before a signal sampler to restrict the bandwidth of a signal to satisfy the Nyquist-Shannon sampling theorem over the band of interest. Since the theorem states that unambiguous reconstruction of the signal from its samples is possible when the power of frequencies above the Nyquist frequency is zero, a brick wall filter is an idealized but impractical AF. A practical AF trades off between bandwidth and aliasing. A practical anti-aliasing filter will typically permit some aliasing to occur or attenuate or otherwise distort some in-band frequencies close to the Nyquist limit. For this reason, many practical systems sample higher than would be theoretically required by a perfect AF in order to ensure that all frequencies of interest can be reconstructed, a practice called oversampling. Optical applications. In the case of optical image sampling, as by image sensors in digital cameras, the anti-aliasing filter is also known as an optical low-pass filter (OLF), blur filter, or a filter. The mathematics of sampling in two spatial dimensions is similar to the mathematics of time-domain sampling, but the filter implementation technologies are different. The typical implementation in digital cameras is two layers of birefringent material such as lithium niobate, which spreads each optical point into a cluster of 4 points. The choice of spot separation for such a filter involves a trade-off among sharpness, aliasing, and fill factor, the ratio of the active refracting area of a microlens array to the total contiguous area occupied by the array. In a monochrome or 3CCD or Foveon X3 camera, the microlens array alone, if near 100% effective, can provide a significant anti-aliasing function. While in color filter array, e.g. Bayer filter cameras, an additional filter is generally needed to reduce aliasing to an acceptable level. The Pentax Caminus 3 from Ricoh introduced a unique sensor-based anti-aliasing filter. The filter works by micro-vibrating the sensor element. The user can turn the vibration on or off, selecting anti-aliasing or no anti-aliasing. Audio applications. Anti-aliasing filters are used at the input of an analog to digital converter. Similar filters are used as reconstruction filters at the output of a digital to analog converter. In the latter case, the filter prevents imaging, the reverse process of aliasing where in-band frequencies are mirrored out of band. Oversampling. With oversampling, a higher intermediate digital sample rate is used so that a nearly ideal digital filter can sharply cut off aliasing near the original low Nyquist frequency and give better phase response, while a much simpler analog filter can stop frequencies above the new higher Nyquist frequency. Because analog filters have relatively high cost and limited performance, relaxing the demands on the analog filter can greatly reduce both aliasing and cost. Furthermore, because some noise is averaged out, the higher sampling rate can moderately improve signal-to-noise ratio. Alternatively, a signal may be intentionally sampled at a higher rate to reduce the requirements on the anti-alias filter. For example, CD audio typically extends up to 20 kHz, but is sampled with a 22.5 kHz Nyquist rate. By sampling at a rate 2.5 kHz higher than the Nyquist-Shannon sampling theorem calls for, both aliasing and attenuation of higher audio frequencies can be prevented even with less than ideal filters. Bandpass signals. Often, an anti-aliasing filter is a low-pass filter. This is not a requirement, however. Generalizations of the Nyquist-Shannon sampling theorem allow sampling of other band-limited passband signals instead of baseband signals. For signals that are bandwidth limited, but not centered at zero, a bandpass filter can be used as an anti-aliasing filter. For example, this could be done with a single sideband modulated or frequency modulated signal. If one desired to sample an FM radio broadcast centered at 87.9 MHz and band limited to a 200 kHz band, then an appropriate anti-alias filter would be centered on 87.9 MHz with 200 kHz bandwidth or passband of 87.8 MHz to 88.0 MHz. Signal overload. It is very important to avoid input signal overload when using an anti-aliasing filter. If the signal is strong enough, it can cause clipping at the analog to digital converter, even after filtering. When distortion due to clipping occurs after the anti-aliasing filter, it can create components outside the passband of the anti-aliasing filter. These components can then alias, causing the reproduction of other non-harmonically related frequencies.